Hello, and welcome to a discussion of enthalpy. At this point, we've learned about heat. We know about heat transfer. We put a metal object into water and saw how the heat transferred from the hot metal to the water. We took heat out of the ice cream mixture and melted water and ice that were mixed together and froze the ice cream mixture. Those are all just heat transfers. The heat, which is coming from the motion of the particles, is transferring. But now we're going to talk about chemical reactions. Chemical reactions, new ball game. Okay? It's not talking about heat transferring. Now we're going to be talking about heat and where is it coming from. Okay? That's just what I just summed up. Heat comes in a chemical reaction comes from breaking bonds. Okay? If you've ever played with Legos, you know that in order to get them apart, you have to put a little force into them, right? You have to put some effort into it to break them apart. Same thing with breaking bonds. Oops, I dropped a Lego. Same thing with breaking bonds. You have to put energy in to break bonds. Therefore, if we're putting energy into something, it's an endothermic reaction. When the bonds reform, they release energy. Okay? That part is exothermic. Depending on how much energy you had to put in and how much energy you're taking out will determine whether your equation overall, your reaction, is endothermic or exothermic. Let's see how this works. Okay? We're going to calculate the bonds. We can figure out the energy of a specific bond. We'll calculate the bonds that are being broken and then subtract from that the bonds that are reformed, new bonds, and we'll figure out the total amount of energy in our reaction. Okay? We use the term enthalpy, though, instead of heat. Enthalpy is actually talking about the total energy of a system, not just the particle movement. Okay? It takes into consideration pressure and volume. We aren't going to worry about that because we're going to assume everything we do is at constant pressure and volume. So for now, our enthalpy, which is represented by an H, why? Same reason heat is represented by a Q. But for now, the change in enthalpy is going to be equal to Q. And we'll use the MCAT, mass times specific heat times temperature change, to calculate some of our enthalpies. Okay? But we'll just be, instead of calling it heat energy, we'll be calling it enthalpy. Same thing, though, basically. Here is a table with some average bond energies. You can see up here, hydrogen bonded to another hydrogen has an energy of 436 kilojoules for every mole. So for every mole of hydrogen bonded to another hydrogen, if you were to break all those bonds, you would need 436 kilojoules of energy. Hydrogen in a chlorine, same story, 431 for 1 mole. Notice, as we move on over here to the third column, a double bonded carbon is 614 kilojoules per mole, whereas the single bonded, which is right back here, is 348. So a double bond requires more energy to break. That makes sense because those double bonds are, let's see, do I still have the example right here? Those double bonds are not going to twist around. Here's a molecule with a double bond in it, and the double bonds aren't going to twist around, whereas I can twist this guy. So, that's why. Triple bonds, even more. So, we have an example here. I don't know how well you'll be able to read that. Let me just do this. Okay, it's probably a little blurry, but it's a little bigger. So we have an example. H2, hydrogen, elemental hydrogen, is going to be one hydrogen bonded to another. F2, elemental fluorine, is going to be one fluorine bonded to another. Okay? On the other side of the equation, we're going to make two hydrogen fluorides. So if we scroll back up and look, hydrogen bonded to hydrogen, 436 kilojoules per 1 mole. So to break this bond, it's going to be 436 kilojoules in 1 mole. Turn that off. And if we scroll back up and look at the fluorine, it's 155 kilojoules in 1 mole. Well, I thought I turned it off. 155 kilojoules per mole. So that's the total amount of energy. If we add those two together, we're going to get the total energy that we had to put into the hydrogen and the fluorine to break them. 436 plus 155. Oops. 591 kilojoules per mole. 591 kilojoules per mole. Okay? Now let's figure out how much energy is going to be released when they realign. Okay? Hydrogen and fluorine, 567 kilojoules per mole. And we have two of them. 2 times 567 kilojoules per mole. 567 times 2. 1134. Now, the way we do this, the bonds broken in the reactants minus the bonds that were formed from the products, 591 minus 1134 gives us a total of negative 500 and, now I've already forgotten it. No one's surprised about that. Negative 543 kilojoules per mole. So for every one of these reactions, you're going to get that much released. Okay? Let's try some more. Yeah. You'll notice, the last one, I drew out the molecular formulas, the Lewis structures, if you will. This one's already drawn out for you. This would be, you have a carbon, CH3OH, this is methanol. Two methanols will decompose into C2H6O, which is not decomposed. They will, well, yeah, they would be rearranging themselves. That's going to be a ester of some kind, and I'm not going to try and name it because I'll say it wrong, plus a water. Okay, but notice how much easier it is to identify your bond, the bonds that you need to count. Okay, in this first compound, we have 1, 2, 3, 4, 5, 6 CHs. So we're going to have to multiply 6 times whatever the energy that's going to take to break that bond. CH, 413. All right, now we also have a CO, and we have two of them. So we look up here, CO, 358. We have an OH. OH is 463. Okay, so now, I'm going to move that down a little bit so I don't have to go back and forth so much. These three are we're going to add up, and we'll get the total energy to break those bonds. Ready? 6 times, now notice I'm going to do the parentheses here. Oh, no, not yet. 6 times 413, 2478, plus, and I'll do parentheses here, 2 times 358, plus 2 times 463 equals 3,194. The other side, we've got 1, 2, 3, 4, 5, 6 carbon hydrogens. We've got 1, 2 carbon oxygens. Oh, look at what this is going to do. Okay, this is kind of funny. And 2 hydrogen oxygens. How much energy are those bonds going to form? Anybody want to make a prediction real quick? Has anybody noticed what's going on yet? To form carbon hydrogen, we're going to need 413 kilojoules per mole. To form carbon and oxygen, we're going to need 358. And to form hydrogen oxygen, we will need 463. Now, guess what? That all is going to add up to the same thing. Bad example to choose. But this minus this would be 0. So this reaction here probably is, I don't want to say it's not going to happen, but it's not going to give off any energy, and it's not going to take a whole lot of energy. Okay? Here's a diagram. This is in your notes, but this is a little bit different. If you think of this as energy here, and this is time, if our reactants are right here, and we put energy in and start breaking those bonds. Okay, we've put a lot of energy in. We get up here, at this point, they're all atoms whirling around. And they begin to bump into other atoms and find a more pleasing way to arrange themselves. And they begin to form bonds. Once they have all formed a bond, they're going to be releasing that energy. If the energy they release is greater than the energy it took to get them started, in other words, we have extra energy here, it's an exothermic reaction. That makes sense. We've been talking about exothermic energy given off. If that's the case, then what's our energy going to look like, our diagram going to look like for endothermic? Well, here you go. We put a lot of energy into the reactants. We don't ever quite get back to where we started. Therefore, we're going to have a net in amount of energy that we had to put in. So when we have our reactants and our products don't come back to the original starting point, we have an endothermic reaction. All right, to sum this up, the reactants subtract the products for your bond energies to figure out the energy of an equation, of reaction. There are other ways that we can do this, but this is where we're going to stop now.